we'll start. So, welcome to my talk, Jailbreaking the AppleTV3. I'm going to tell you tales from a full stack hack. So we will have quite a few exploits in this talk, but this is not mainly an exploit talk. It's mainly like about the story behind it and developing the full thing and putting it together. So my target was the AppleTV3, which is Apple's third generation set-top box. It was released in March 2012, which is a fairly old device. It runs a stripped-down version of iOS, so very small attack surface. And the first public hack was almost 8 years later. So I guess the first question comes into your mind, well, why is that? So let's take a step back. The first generation Apple TV was released in March 2007, which was actually an Intel x86 CPU, and that ran a custom version of OS X Tiger. And unofficially, you could run Linux, so this one didn't really need to be hacked in that sense. The Apple TV second generation was released in September 2010. It has an ARM CPU, which was the Apple A4, same as like the iPhone 4, and it runs a custom version of iOS. This one was vulnerable to the limerain boot ROM exploit, so there were also several jailbreaks for this. The next Apple TV, which was the Apple TV 4th generation, was released in September 2015, had a 64-bit ARM CPU. This one runs tvOS, which is kind of just now its own iOS branch, and this one can run custom apps, while the ones before, like the second and the third gen, they could not run any custom apps. So here with custom apps, you can again do the app-based jailbreaks. There were various jailbreaks for that. It is also vulnerable to the checkmate boot ROM exploit, and this was actually hacked before the Apple TV3, mainly due to the custom apps. Our target here, the third gen, no boot ROM exploit at the time. Now there is checkmate, although there's two different versions of the Apple TV. There's the 3.1, the older one, and the 3.2, the newer one. The newer one you can exploit with checkmate using a computer. The older one you can actually not exploit using a computer, but you need something like an Arduino. So using software approach for this is still kind of better. It does not have custom apps, and it runs much less services than on the iPhone, so very reduced attack surface compared to the iPhone. It's essentially a web browser hooked up to your TV, and the apps that are there, it's mostly just a custom XML scheme. It's not even HTML, it's just some custom XML, and a custom JavaScript thingy. This is what the Apple TV3 home screen looks like. So these apps are just like web stuff. So there's this thing for the Apple TV3 called PlexConnect, which was previously the only, in quotes, hack for the Apple TV. What you could do is you could set up a custom DNS server and redirect the IP for the Trailers app to your server. And then if you open up the Trailers app, it would actually render whatever XML you put there. At some point, they switched to HTTPS, so you had to manually trust a TLS certificate, and you could still do the same thing. So you could control what the browser displays, and what you can do is you surf your own mediathek and view movies from your own server and stuff like that. By serving XML and JavaScript. So usually you navigate using the up, down, left, right, and the button in the center. Although there's a hidden menu, if you go to the settings, hover over send data to Apple, you press the play button instead of the OK button in the center of the remote, you would get to a hidden menu where you can add profiles. And here you can type in the URL of a certificate, and it would trust that certificate, and you can use that to view your own HTTPS website. So that's how the PlexConnect thing works. So again, the Apple TV3 is like a custom-ish browser, which is based on WebKit, but it does not render HTML, it renders some custom XML scheme. It has a custom JavaScript with global predefined ATV object. And it also has a somewhat stripped down JavaScript, so not all functionality is available. And unfortunately for us, there is no JIT. Yeah. So let's get to hacking. How etason ATV kind of works. So what we're going to first do is set up a custom DNS server, which will redirect trailer.apple.com to a controlled server. We trust our self-signed certificate so we can actually display stuff in the browser. And then we visit the trailers app. Once we do that, the TV sends out the request to that URL, and then AppleTV/US/JS application.js, and first fetches this JavaScript file. And this is a sample taken from the PlexConnect from the GitHub repo. This is what they implement. And there are several custom callbacks. So the interesting thing here, if you don't see the code, that's totally fine. There is the ATV on app entry, which if you set it to a function, this function is called as soon as that thing is loaded. And you can also do ATV load URL to load a custom XML thing. And if we do that, we can actually load a screen. So this is like to the right, my XML page, and to the left, how it is rendered on the Apple TV. And the interesting thing here, what we can do is we can put on a script tag and import a JavaScript file. And there's also like the buttons. We can say, okay, on click, we call this JavaScript function. And this is how we kind of get started. So now to the exploit.js. Basically, what we want to do is we want to download a stage 1 binary.bin. This is what I call it, and a bootstrap. But there is no binary download available. Okay, fine. So we can just encode the files in base64 before serving them. And you would think that JavaScript can do that, but the Apple TV can't. So you need to manually write a base64 decoder, which is fine. So that's what I did. To the actual bug, so I was like at CCC and I talked to some friends and was like, hey, what should I use to hack the Apple TV since it doesn't have JIT? And he pointed me to this presentation of KeenLab from POC 2016, and he said, this is the POC, this is what you need, that you can overlap a UN32 array with an array, and then you can do magic JavaScript stuff. I'm not really good at browser exploitation, but that got me poking around, and I could get the exploit working. So basically, you can leak pointers to objects, and if you do that, you can leak pointers to WebKit, you can leak pointers to DYLD shared cache. This is where all the libraries are mapped into the iOS process. It's a huge blob. Then you can leak the ASLR slide. If you smash the UN32 JavaScript object, they have a pointer and to a buffer and the length. And if you set that pointer to 0 and the length to OXFFFF, the array now is your full virtual address space. So through that JavaScript UN32 object, you can just read and write virtual memory in this process, which is good. So we can now use these primitives to build the ROP chain and write them in some virtual memory with the UN32 array. And we can corrupt a JavaScript function object and stack pivot to the ROP chain and execute that. And if you want to know how more details on that, there is a very good video by Live Overflow. It's called What Do Nintendo Switch and iOS 9.3 Have in Common? It's not exactly this exploit, but it covers like after the entry the other ideas. So this is a good resource if you want to look at it in more detail. Problems on doing the actual exploit. So we don't have any binaries. How do we build a ROP chain if we don't know any binaries, if we don't know any addresses, even though we know the ASLR slide, we don't know what is where, basically. Okay, well, look at firmware update files, but these are encrypted, and unfortunately the keys are not available, and were not available at that time, and let's assume we just don't have keys. We can dump memory, but okay, where do we dump memory? Easy. We have Crashlogs. Crashlogs on iOS tell you actually a lot. They tell you the fault address, where the exception happened. They give you a backtrace of all the threads running, and see like backtrace of all threads. You get the full register state of the crashed thread, and you get all mapped libraries into that process. So here's, if you don't know, in iOS you have the shared cache, which is a big chunk with all the libraries in the system, which is mapped into each process. And this is randomized once at boot. So if the process crashes and restarts, these ones stay actually at the same position. So you can let it crash once, grab the log, get the address, and then you know where to dump and where to do things. Now, how do you actually get the crash logs from the device? So there is this tool, iDevice Crash Report, by the libmobile device project. This requires a USB connection. The problem is, as you can see, or maybe not, it is very close, the micro USB port to the HDMI port. So you can't really plug in both cables at once because they don't fit. So we need to do some hardware hacking to actually overcome this problem. And this is how I solved the issue. Yeah, and then you can stick both in. So now, with the newer updates in the libmobile device project, you can actually grab the logs via Wi-Fi 2. So you connect it once, pair it, and then you can actually go over Wi-Fi, and you don't need that, but back then you needed like both cables. So let's dump some memory. We know what we want to dump. Why? Okay, so we want to dump lib system kernel dylib. Why? Because there are all the syscalls, and so we can just rob there for all the kernel syscalls that we need. We want to dump lib avf audio dylib. It just happens to have the greatest gadgets for exploitation. Really, really handy. And we want to dump the addressbook.framework. You will see why we need this one in a few slides. But I chose this one because we hope it is unused on the Apple TV, because why would you need an address book on a TV setup box? So I assume it's unused, and that's why I picked this one in particular. And we know where to dump through the Crashlog mappings. So how do we dump memory? We just read from the UN32 array in JavaScript. We encode it to hex bytes and then send a GET request to our server. And on the server side, I have like a Python Flask server, which just writes it to a file and like does the hex back to binary and writes it to a file. And then I specify the dump address, the dump size, run it, and dump. I also implemented the log function because you wanted to do logging during the exploit, but you don't actually get any logs from your state of the JavaScript exploit. But what you can do is you can again send log requests to your server and then look at the GET requests, and then you can use that for logging. Also, I implemented a function load binary, which doesn't really load binary. But yeah, I needed a way to transfer a file from a computer, which I encode base64, then decode it, and then store it in memory for later use, which is for my stage 1 and for the bootstrap, which I need later. So far so good. So you would assume I just run it and dump it, but the app crashes after dumping 2 kilobytes. I don't know why, and I was like, what do I do? And I guess as a hacker, you know, there's exactly 2 options. One is you track down the root cause of the problem, fix it, and you have a proper binary dumping thing. Or the other is you go for a terrible workaround. So, guess what I chose? There is a GitHub project which is called pwning, which emulates a Apple TV remote. So you pair that program with the Apple TV, and then you can write a Python script to push buttons on the remote, and it would do things. And I just coded a Python script which presses the down button, which presses the select button, which waits 15 seconds and repeats. And can Yeah. So this is what it looks like. And you can dump like 3 kilobytes before it crashes in like 15 seconds, which is like 200 bytes per second. So this really takes a bit. I first wanted to dump the whole shared cache, which is like a few gigabytes, like 2 or 3 or something like that. But I just gave up on that and just only dumped this 3 specific libraries that I showed you before. It's still, I was doing dumps for like a week or so until I decided to focus on just these things. Okay, so we know what we need to do. And we could do like ROP, but what we really want to do is actually code our further stages in C. iOS has mandatory code signing, so you cannot simply map like a page of memory, write your code to it, make it executable, and jump to it. Because code signing blocks that. Unless you use a code signing bypass. And in this jailbreak, I used the code signing bypass that Max Basali presented in DEFCON 24, which is basically, so the code signing checks were checked when the page faults. So what he would do is he map it, and then he mlock it, and then he mprotect it, and then somehow that would prevent the fault triggering the code signing check. So you are back to, okay, we can actually now, with that bypass, map memory, make it executable, and jump to it. So this is what we continue. So our ROP payload needs to execute this code signing bypass and then jump to it, and then we do more stuff. So earlier I said we have this stage 1.bin, which is compiled as raw binary. So the first 4 bytes is the size of the code section. Then we have the actual code, which is goes up to a page boundary. And then we have the data section of the code. So I just code it in C, compile it, script these sections, put it back as a raw binary, and this is what I get. ROP chain in JavaScript is super easy because you can do all the computation in JavaScript itself. And we use the code signing bypass, which again just jumps to the start of stage 1.bin. And this is the whole function which does the ROP chain building. So basically it's 3 calls. It's mmap, the full size of the binary. Then we mlock it. Then we mprotect just the first code part. And we can just jump to it. That's it. So easy ROP from JavaScript. And ROP is, yeah, this is what the mprotect call looks like. You just have your stack buffer and you write the addresses, add the slides from inside JavaScript. Super easy. I did run into a few problems though. So on ARM, if you have very short functions, then they don't actually push the return address on the stack. So you don't need to do that if you don't call any subroutines. So these ones, so when you call a function, it ends up in the link register, and when you want to go back, you just go back to whatever the link register points to. If you call subroutines, you would store the link register on the stack, and at the end pop it into the program counter. But very short ones don't actually pop that, so if you were to call that from a ROP chain, how do you continue from here? Because you don't really control the contents of the link register, right? But there is a very clever solution, and this is why we needed the address book framework. Basically, what you want to do in the address book framework, you look for functions which do call lazy link functions and then return, which is like the last thing they do. So you have call the function which is lazy linked, and then just pop the PC from stack. So that lazy link function in that library is actually a little stop, which loads a pointer from memory and then jumps to it. And that pointer is like in the global offset table section, whatever. So you can write your next stage pointer to that. And this is what we called, so this is, So you write the pointer there to that previous function, which we couldn't call before, mprotect. So we put the pointer there and we jump here, and it will call mprotect, jump back here, and then pop the next thing from the stack. Yeah, lazy link stop. Yeah, also you want to make sure when you do that, that other threads don't actually rely on that, because if you just overwrite, then the random thread might crash the process, which you don't want. This is why we use address book framework, because hopefully it's unused in the web browser on an AppleTV. So what does stage 1.bin do? So we just jump straight to it without any context, so it just doesn't know where it's at and what it does. So we want to brute force the ASLR slide, which on 32-bit is very simple. If you have already code execution, basically what you can do is you use, I don't know, like the chmod call. What does chmod call do? You give it a string and permissions. But what is a string really? It's just a pointer to memory. So there's two different error codes which chmod returns. The one is like the file doesn't exist, and the other is this memory is not valid. So by looking at the error codes, you can actually go page-wise the address space up until it gets you from the this is not a valid address into okay, this is not the valid file, and then you know okay, this is the base address, and from that you get the slide of the dynamic linker. If we have the slide of the dynamic linker, which is mapped into the process, we can resolve the symbols for dlopen and dlsim. And from there, all external library calls we can just manually link ourselves by calling dlopen to get the library and then dlsim to link that function, and then just call the functions via going through that function pointer. Yeah. So after we've done that, we repair the stack. We set it like at the end of the data section, so we don't work with the corrupted stack, so we have a clean stack again. And then we manually link all external functions, and then we suspend all other threads, because remember, we are from a web browser context, and there are different threads. And for our next stages, we don't want any other threads to interfering with whatever this process does or with whatever the kernel does. Yeah. I actually did a write-up on this exact thing, so if you want to check it out, it's Modern Post-Exploitation Techniques on my blog. Yeah. For the kernel exploit, I'm using the Pegasus Trident bugs from back in iOS 9, because this is like the iOS 8 running here, so these are still there, which is an info leak, which gives you KSLR bypass and the memory corruption. I won't go too much into detail into this, because this have been talked about by Max Bazelli several times, and there's a lot of good blog posts and researches, but I just used some old bugs to get into that. The problem here is we don't have a kernel binary, so how do we actually know the offsets we need for the exploit? Well, there's essentially three methods we could do. We could use other kernels as template and then guess like the difference and see until we hit it right. It's a bit tedious, but it's doable. We can port the checkmate exploit now that was out already and just decrypt the kernel. But then again, for the AppleTV3, this is not as trivial because it requires like Arduino hardware with high control. And this is like also a different project, so I didn't really want to do that. The other thing is we could try to dump the kernel, and this was actually described also by Max Bazelli in his talk. Basically, through the specific means of this exploit, it was possible to, so the bug is in OS unserialized binary, you deallocate string, you can call retain, and then you can get code exec. And if you, we already have the KSLR slide, so we can crash at a specific position, and that would appear in the kernel crash log. So you could, by that, dump 4 bytes at a time and then reboot the device, and then again crash at a different position, look at the log, and dump 4 bytes at a time. Yeah. And then once you do that a bit, you go for a specific object, which is in that case OS string, and then you can use to dump the kernel a bit faster. So this is what he did with the Apple Watch jailbreak. Luckily, if you just download the latest kernel for this specific device, which is some iOS 8 something, they stopped encrypting the kernels anymore. They still encrypt the bootloaders, but the kernels are no longer encrypted, so I actually did not have to deal with that. But if you were to deal with that, this is like some options you could do. Okay, so I will skip over all the exploit part for the kernel and jump straight to the post-exploit. So assuming we got our kernel read-write primitive, we patched all the kernel functions to disable code signing, to disable sandboxing, to elevate our privileges to root, to escape sandbox and everything. And we're back, and we're now at the post-exploit stage. So previously, from the JavaScript context, we downloaded the bootstrap binary, and we stored that into an array. And since we could leak the pointer of that JavaScript array, we stored that right before our payload, which we mapped and written in C. So from inside the C payload, we can go back, okay, look, the code is here. So we come back at the beginning, and then there we find the pointer to that JavaScript object, which is still memory. And from there, we find that array, and from there, we can just read that and write it to a file. And then we can just execute that file, and it runs a binary. Since we already disabled the code signing check, it just runs. So that post-exploit thing checks whether... so before we actually run it, we check whether mkdir exists, because on normal systems it does not exist. But after we extracted our bootstrap and installed like core utils and SSH and everything, we have the mkdir binary. So if it does not exist, we write that bootstrap to a file and just run it. And if it does exist, then we're rerunning this, and we don't need to re-extract the bootstrap again. So the bootstrap itself is written in Objective-C, which is mainly because I didn't want to because I wanted to download more stuff, and I didn't want to do that from C because of libcurl wasn't like trivially in there. And from Objective-C, it was super easy to use NSURL and context from URL and stuff like that. So I used that to download tar, launchctl, cdr.tar, and untethered app. So cdr.tar is basically all the core utils, it's bash, it's OpenSSH, and whatever else you need. This is just gets straight up extracted to the root file system. And then we run user libxx cydia startup, which sets up a few files for like the jailbreak environment. Then we also install the untethered app. I run dpkg-i untethered app. It does not work for some reason. And I didn't really feel like figuring out why it doesn't work. So I was like, okay, I just copy it to var root, and if the user SSH is in, we can manually install that. So we shifted that problem. This is now someone else's problem. But there is the untethered app. You just need to log in and install that. This also leaves you the option to not have it untethered. If you just don't do that, then when you reboot, you will get back to stock, and you just need to rerun the web exploit. So what do we do post-bootstrap? Well, first we need to clean up the kernel exploit, so the kernel and the device doesn't crash and the device doesn't panic as soon as we exit this process, so we do that. We want to run an SSH daemon, because this is like the main thing I wanted to do with the device, is to get SSH. And we restart the home screen, which is essentially restarting a browser, which you can simply exit it, and then launch daemon will just restart it for you. So this is also super simple. Okay, persistence. So we have a secure boot on iOS, so we cannot just patch the kernel on the file system, because then the bootloader verifies iboot verifies the kernel, and then like if any of these are tampered with, it will refuse to boot. So we actually SSH won't run after reboot because it doesn't have a valid code signature and so on. And rerunning the exploit.3 trailer app every time kind of sucks, and I need to automate that to exploit that at boot every time automatically. So ideally, so this is what an untether is. Okay, so in iOS, the boot sequence starts a daemon at some point in the boot sequence, which is called rtbuddyD. I did never look into what it's actually doing, but we know that launchctl starts it with the parameters -- early boot. There is also a binary called JSC, JavaScript core, which is, you can give it a file, and it will execute JavaScript like in a terminal with all the browser overhead. So both of these, well, at least the JavaScript binary exists on the Apple TV, and the other one is called. Whether it exists or does not exist, in our specific case, this binary doesn't actually exist. It only exists on some devices, but LaunchD still tries to run it. So what you can do is you can take the JSC binary and put it where the system expects RTBuddyD. So launchctl will try to call it, and since it's Apple's own binary and has a valid code signature, it will actually run. So launchctl will call RTBuddyD in --early boot, but JSC takes a file as a parameter. So if you call JSC with --early boot, it will try to open and read the file /--early boot. And if you put a JavaScript file there, which doesn't need a code signature, JSC will try to run that JavaScript file. Here, you can exploit the exact same vulnerability that we did before, but since that was taken from a previous project where I used a different web exploit, which was not deterministic, I actually exploited yet another vulnerability in JSC itself, which was also a exploit like the one used here. So we could use the same vulnerability, but here it's actually a different one in JSC itself to get code execution. And we can use pretty much the same payload we used before, because after we jump to our code, we execute the same Kernelexploit again. This time, though, we have JIT, so we can skip the code signing bypass. We just map my memory, read, write, execute, and we're good to go. This is almost it, but there were problems. Obviously, there's problems. So, if we do that, for some reason, we get code execution, we patch the kernel, and then we get root, and launch daemons don't start for some reason. I don't know why. SSH doesn't start, and this was literally the only thing that I wanted to do. I had the same problem on the iPhone before, but there it wasn't so bad, because then you can just manually open the terminal emulator and manually launch SSH, and then it would actually work. We don't really have this ability here, so ideally SSH should start up right away, otherwise we can't really start it up. Again, two options. Do we want to debug the problem properly, or create a workaround so it just starts? Again, I went for option 2, which led me to this complicated graph. So basically, at the root, we have launchd, which starts RTBuddyD, which actually is JSC because we replaced it. And for some reason, everything which comes from that path, which is marked red, it can't talk to launchd, so we can't say, hey, launchd, just start SSH for us. We can spawn the SSH binary manually. That works. And then we can connect, and then we get the bash. But even then, we can't really talk to launchd, and some things seem like fishy and broken, so I did actually want to solve that somewhat properly. Also, we need JSC to return success for boot to continue, because if we hang the JSC binary, then the boot won't continue, and at some point the watchdog will reboot the device, so JSC definitely need to exit cleanly. And, okay, what can we do? Basically, what I ended up doing is in RTBuddyD, I spawn another process called daemon loader. And I use libtakeover, which is a library that I coded, which basically gets a task port to a different process. And with a bit of magic, it can actually call functions in a remote process. So you say, you give it like a function and parameters, and it will call that with a like kidnapped thread on a different process. So you get like function calls and code exec in different processes. So what it does, it gets the task port to syslogd, which is yet another daemon spawned by launchdaemon. And if we ask launchd from inside syslogd to start SSH, that kind of works. So I was like, okay, let's just do that. So daemon loader injects into syslogd and then talks to launchd and says, hey, please launch SSH for me, and then SSH daemon launches correctly, and from there everything works fine. Okay, we're almost at the end of the talk, so let's just recap what happened here. So, we redirected DNS, we trust a self-signed TLS certificate, we spoof the trailers app to open the web page that we presented, we run JavaScript to get ROP code execution, we use ROP to chain load to execute a code signing bypass, to chain load a payload, which we wrote in C. The payload executes a kernel exploit, it patches the kernel, and runs a bootstrap file. This deploys another JavaScript exploit, which runs at every boot, and then again re-executes the kernel exploit. And this essentially is a full untethered jailbreak for the AppleTV3, and that lets you SSH into your Apple TV. Now, you may be thinking, what can I do with a jailbroken Apple TV? My answer would be, I have no idea. Like, why? Like, I just wanted to have like the SSH shell, and then it's old, and you could run Kodi on it, but this is so old that like no one really bothers, and it doesn't have any real use cases. This was my answer when I prepared the presentation earlier. So actually, I have a very good reason to put all this effort to jailbreak your Apple TV. So basically, if you've used an Apple TV and you let it sit around for a while, at some point there is a screensaver. And what you can do is you can, since you had root access to the files, you can replace the files with funny cat pictures. This is why we're doing it. All right. Now, do you have any questions?
Okay, so that was a really long chain of exploits that he had. Like, even the summary slide was really long. So did you get stuck on any one of them more than the others? Like, was any one particularly difficult to overcome?
So this was actually a lot of sub-projects. I didn't like code them in one go. So I first started with the app-based jailbreak for iOS 9, which just did the kernel exploits. At some point I was like, okay, I want to do the untether, so I then only did the JSC thing. At some point I was like, okay, but now I have like most of the JavaScript ready. I want to do like the remote code execution, so I implemented the jailbreak me for iOS 9. And most of the chunks I had already done, and I had like very minor changes. And for this specific thing, I had to swap out the entry WebKit exploit for the JavaScript stuff, but then I can also copy and paste a lot of things, had barely changed a few offset, and just work. So this is actually like multiple projects that chain together. And the fun part was like chaining these together and doing it specifically on the Apple TV.
Were entitlements a thing in iOS 9? And if so, would the code signing bypass the task for PID entitlement?
So entitlements were a thing, but the code signing bypass, so if I understand correctly, whether I would need entitlements to run, okay, no, because this was like yet another bug, technically, which was exploited. So by unlocking the memory region, we would avoid the check for the code signature in the first place. So this is yet another bug which was also patched in iOS 9.3.5. So the fun part of doing like these very old devices, you have a huge load of bugs already available, and you just pick whatever bug you need, and then you may or may not need to write an exploit, then you chain that together, and this is like a lot of fun to me.
How long did it take you to do all the research until you got it working?
Again, this is hard to answer because there were lots of sub-projects involved, which I did while trying to procrastinate not to learn for my exams at university. So it's not like a start-to-finish project. It was like, now I'm doing this, and at some point, okay, this, the next one, and then this one, and just chaining together. So I have no idea how much I spent there in total. It was quite a bit of work, but it's also like fun and relaxing. Any more questions? Okay, if you want to ask me anything, feel free to chat with me. I'm still around.